This is a B2 video from the topic organisation looking at blood. Now, if the doctor takes a sample of blood from you, then it could be put in this machine called a centrifuge in the lab. And what this does is it separates the blood based on density. And it could be that there is a particular hormone that the doctor wants your blood tested for. And we know that hormones travel in the plasma, so therefore separating the blood, we can just test the plasma rather than the whole blood. Okay, so the red blood cells are the densest, they sink to the bottom. Plasma is the least dense, that rises to the top. Okay, it's also really useful to see the proportions of each part of the blood compared to each other. So let's look at red blood cells first. They have this biconcave shape, so it's kind of squished in the middle. That increases the surface area of the blood to allow more oxygen to be absorbed. No nucleus, because it just takes up space. And the oxygen combines with hemoglobin to make oxyhemoglobin. Okay, and it's only the oxygen that's carried in the red blood cells. Okay, no carbon dioxide, just oxygen. However, saying that, if you have a faulty gas boiler and it's leaking carbon monoxide can be absorbed by those red blood cells more easily than oxygen can be. Okay, so if your red blood cells have absorbed lots of carbon monoxide, then it's depriving your cells of oxygen. Okay, because the oxygen can no longer bind to the red blood cells. But what we're going to remember is just red blood cells carry oxygen. Okay, biconcave shape gives it a greater surface area for absorption, and there's no nucleus there. Everything else that the blood could carry is carried in the plasma. Okay, it's about 55% of blood. It's the liquid that makes the blood flow. Carbon dioxide, okay, product of respiration. Digested food, all the stuff we learn in digestion, so the amino acids, the fatty acids, the glycerol, the glucose, okay, all of those small soluble molecules. If you study triple science and you know about the kidneys, the urea is also transported in the plasma. Hormones, that was from paper 2, transported in the plasma. And heat also transported in the plasma. So the heat is when the blood goes close to kind of our fingers under our toes, where there's a large surface area, we lose a lot of heat through those, and it's coming from the plasma. Then we've got the white blood cells. 3 methods of attack of by the white blood cells, and we learn about this in B3. First of all, we've got the ingesting of pathogens, which is phagocytosis. The white blood cells then digest the pathogen using enzymes, keep anything that's useful and reject anything, excrete it out that's not useful. They release antibodies which have a specific shape. They attach to the antigens of the pathogen, making it inactive. And they also release antitoxins which neutralize toxins produced by the pathogen. Platelets are fragments of cells involved in blood clotting and scab forming. So if you cut yourself, then platelets will block that gap, causing a scab to form. Okay, so red blood cells carry oxygen. Everything else is carried in the plasma. White blood cells fight disease. Platelets form scabs. Let's have a look at a foundation level question. The part of the blood that carries oxygen around the body, that's going to be the red blood cells. The part of the blood that protects the body against infection, white blood cells. The plasma, it carries the carbon dioxide, the glucose, the hormones, the urea, and also allows the blood to flow. And we've got a picture from an exam question here. We can see red blood cell, not a great picture, but they've labelled the red blood cell. Small fragment of a cell, so that must be the platelet. The larger cell with this extended nucleus, that's the white blood cell. And then pointing to just the space in between is the plasma, the liquid part of the blood that allows it to flow. So if we wanted to calculate rate of blood flow, we know how much volume of blood has gone through a blood vessel in a particular time. We obviously know the amount of time as well. We could do the amount of blood that's flowed, the volume of blood, divided by the time in minutes that it took for that volume of blood to flow, and it gives us the rate of blood flow per minute. Let's look at a question then. The mean concentration of red blood cells in an adult is 5.5 times 10 to the 6 cells per millimetre cubed. Okay, they say 1 millimetre cubed is equal to 0.000001 decimetre cubed. So I'm doing my own conversion here and saying, okay, well, 1 decimetre cubed, okay, I've moved the decimal point 1, 2, 3, 4, 5, 6 places. Okay, so I need to add 6 zeros onto the end of 1 millimetre cubed. So equivalent, 1 decimetre cubed equals 1,000,000 millimetres cubed. And I need that because it says calculate the mean number of red blood cells in 1 decimetre cubed. Give your answer in standard form. So the first thing I've done is I've taken out of standard form the 5.5 times 10 to the 6, okay, which gives me 5,500,000, okay, 5.5 million. I've multiplied that by the number I came up with here, which told me how many millimetres cubed are in a decimetre cubed. Okay, so I know that there is 5.5 million cells per millimetre cubed, and I know that there are 1,000,000 millimetres cubed in a decimetre cube. So I multiply those together, I get that huge long number, and I put that back into standard form, which is 5.5 times 10 to the 12. Okay, that is the mean number of red blood cells in 1 decimetre cubed. I think the best thing to do is always take the numbers out of standard form and then put them back into it afterwards. But if you're happy doing standard form with your calculator, then by all means do it like that. Okay, one more question. The aorta transports blood from the heart to the body. In a person at rest, blood travels at a mean speed of 10 centimetres per second in the aorta. Blood travels at a mean speed of 0.5 millimetres per second in the capillaries. So straight away I should have alarm bells saying, okay, I've got one number in centimetres per second and one number in millimetres per second. The speed of blood decreases at a rate of 0.4 centimetres per second as blood travels from the aorta to the capillaries. So I've got 2 of my numbers have centimetres in, 1 has millimetres in. Okay, calculate the time it takes for blood to travel from the aorta to the capillaries. Assume the speed of blood decreases at a constant rate. They've given me an equation and they've said give my answer to 2 significant figures. Okay, now this 0.5 millimetres per second can be converted to 0.05 centimetres per second. Okay, that's my conversion, gets everything into centimetres. So that's my first mark, converting the 0.5 millimetres per second to 0.05 centimetres per second. Okay, then the equation said find the change in speed. So if I've got the speed at 10 centimetres per second in the aorta and 0.05 centimetres per second in the capillaries, the change in speed is the larger number minus the smaller number, and then I'm dividing it by the rate. Okay, so I've had to rearrange the equation as well. Lots of things going on here. Okay, so I've swapped time and rate of decrease in speed over. So I'm now dividing it by the rate of decrease in speed, which is 0.4 centimetres per second. That gives me 24.875. Okay, now go back to the question. It says give your answer to 2 significant figures, not 2 decimal places, 2 significant figures. So because I've got 24.8, 8 is it's a 0.5 or over because it's 0.8. So I'm going to be rounding it to 2 significant figures to 25. Okay, so 1 mark I did my transfer my millimetres per second to centimetres per second. I rearranged my equation and then substituted my numbers in. I got my answer and then I rounded to 2 significant figures. Hope you found that useful. Thank you.